and linear transformation is continuous, so it works.
Yeah.
Okay, so today we will embark on the next chapter, and I have already given the first few things, so I'm going to just mention briefly about them. So from now on we'll be talking more applications of what we have constructed. So applications of differential calculus. Differential calculus. Okay, so first few things is that it has applications in PDE, means partial differential equations. So first thing is, so this is our heading, and first thing is this PDE. So topic is PD, partial differential equation. Okay, so that's the first application of differential calculus. So an equation involving a scalar field and its partial derivatives is called a partial differential equation. So for example, this is one of them. Okay, this is one example. This is another example. Suppressing again xy is there. Okay. So these two can be said they are linear partial differential equation. They are also homogeneous because there are no higher orders. All of them are the same, dx squared, dy squared, dx. So all the derivative operators are of the same degree, or you can say order here, of the same order. So each of these homogeneous PDE, linear PDE, homogeneous and they're linear. Linear because, why is it linear? Can you please say why it's linear?
Because the dependent variable has power 1 at the highest derivative.
You do not have terms like this kind of terms. You do not have any this kind of terms.
No, we can have these kind of terms because they are independent variables.
Who are independent variables?
X and Y are independent variables, right?
But you cannot have, okay, maybe you cannot have this. Okay, so
we cannot have x squared.
You cannot have this term. Yeah. But your question is, you can have, yes, you can have xf terms. Yeah, but you can have xf terms, right? Okay, but you cannot have terms like f df dx, or you cannot have df dx squared term. This is nonlinear. This is nonlinear, yeah. So how does yeah?
Linear systems.
Yes, all of them are same. Linear algebra, linear systems, they all mean the same thing.
It's not about the differentials. How the system input the verdict.
Yeah, well, so in the differential equation you have these things. Yeah, so it describes a system, and you can, so the disturbance can be a source term in the differential equation, right? Yeah. So obviously this kind of squared terms, if you have a nonlinear squared term, that's a nonlinear term. You cannot have a nonlinear term there. You cannot have any f power there.
Any square term is non-linear.
Any square term is nonlinear, however, of the dependent variable, not of the independent variable. Okay, so this independent variable is all right, as Riaz was talking about. This is all right. However, this is not all right. This is not all right. This is all right. Okay. So you cannot have any higher order terms in the dependent variable. Okay. So for example, let us look at some of the examples here.
An equation involving vectors, what does it mean?
So suppose this is a linear equation. However, if I put a square, this is not a linear equation anymore. Okay. Yeah, what I put a vector field? These are scalar fields. We specifically mentioned it as scalar field. Okay. So PDE generally is a scalar field.
But system of PDEs we get.
Yeah, well, then you can group them together. If you have a system, you can always write it in terms of matrices and all that. That's true. That's true. Okay. Right.
Scalar fields meaning constant value or something like that.
Scalar, what? Constant value? No, scalar, what is scalar field?
Yes, I was talking.
Yeah, scalar field means it's just a, okay, so it takes input in Rn and outputs a real number.
Oh, that's it.
Yeah, it's just one, it's a real output. Yeah, so that's gone. So another example could be, this is familiar from physics.
Sorry, does it mean that we
Yeah.
can have a vector field for Russian differential equation? We can have, because we can have system of
We can have vector field.
So like equation involving a scalar field. So if we write that an equation involving a vector field, that will become
Well, the vector field is that it's not a PDE in the usual sense. It's not a PDE in the usual sense. In the usual sense. A PDE as a definition is an equation of a scalar field. Yeah. So this is an equation of a simple harmonic constant. Yeah. I don't think you can. I'm sorry. I think I have to think about this one. So if you talk about Newton's equation, what is that? dv dx is equal to md square x dt square. No.
Yes, yes, linear equation.
Yeah, linear. What does it mean by linear? So I have to just comment on this one a little bit. If this is not linear. This is not linear equation. This is a non. Why is non-linear? Because the potential can be non-linear. Okay. So what does it mean by linear? Let's just understand in terms of equations. What does it mean by a linear equation? I think I'm not going to be comfortable with this one. পড়ে গেছে কোথাও। Cancel now. What does it mean by having a linearity? So if you have a linearity, what does that mean? So you have a linear operator acting on f equal to 0. So the operator has some linearity property. What does it mean? It means that if you act on this, it should be LF to begin with. And the second thing should be L of f plus g. There should be L of f plus L of g, no? These properties. Yeah. So this thing can be written as, say, I'm equal to 1. Then I say d square dt square, and yeah, so v. So if I take it on this side, this will be v acting on x is equal to 0. No, I'm sorry. Yeah. So this is so now we can test linearity of this thing. No, now how do we test it? So this is our L. So if I multiply a times x and take L on it, okay, that means the d square dt square ax plus v of ax. So this is this, no? Suppose I take a nonlinear v of x term. Say this form is say a square x square. When it's a x square function, v of x is a potential which is say x to the power n, more general. Say. You can do that, no? Some polynomial in x. Okay, so then this should be a n x to the power n. Now this is not linear. Yes, so this kind of x squared term cannot also be there. You cannot have any higher order terms.
Can you please explain what operations did you use to reduce the x partial derivative?
I'm sorry. Oh yeah, dvdx. Yeah. Well, yeah. So dvdx. Yeah.
And
Yeah. I missed that one. Yeah. I'm sorry.
can take x common also. But the operator is not acting on the same variable, the operator. Right.
No, it's acting on the same variable. So you can just dvdx. You can say it's it's acting on the same variable.
Or
So
you get this.
you can substitute this one here, d square dt square plus. So if you put n x to the power n minus 1 and x equal to 0. Okay, so you just go through it. Okay, do not write the repetition, just go through it, act on x, write the form so that it avoids all the confusion. Yeah, so it cannot, you can just look at this and you can say this is not true. Thank you, I forgot the x. I just went for the Schrodinger equation. You have a v and I went with that, so there is a derivative there. Subtlety, sorry. So in Schrodinger equation, I could have done it for Schrodinger equation. What is the Schrodinger equation? Yeah, so there is an I is equal to, say I am doing the, so Laplace here for 1D, say. Okay, I'm throwing all the constants of, and this is Schrodinger equation. Okay, yeah, and
We always need to include the I, but you are throwing all the constants. But we always need to include the I, even if you are throwing all the constants.
yeah, I have the I.
Why do we need the I?
Because I is very important. I must be there. I is not a constant. It's not just a constant. Without the I, this can have real. This is the real. This is over the real. With the I, it's never on the real.
Without the I, it's like equation.
Yeah, means over the complex field. So with the I, it's a complex field. Without the I, it's not the same. It's explicitly on the complex field. Very good. So I can have a potential there, no? No, it's a linear system. Linear system. Okay. It's because the psi is an eigenfunction of x. Okay. So psi is a solution of this. Okay. So for the x's actually. Yeah.
That will be divert our topic.
Yeah.
But I have a question like, why do we always opt for eigenvalue solutions in Schrodinger equation? This thing actually takes me like, why do you always opt for eigenvalue solutions? Is it because I have an answer, but I don't think it's a really good one.
Why we opt for eigenvalue solutions?
Yeah, why you always opt for eigenvalue?
This is the Schrodinger equation. However, if you demand that your space and time can be separated.
Yeah,
okay.
That's the logic I know. But
yeah.
I heard some other logics as well that you can mathematically map quantumness by eigenvalue problem.
No, this is the main reason. If you can separate variables, then you can reduce the problem of a time dependent. It is the Schrodinger equation. This is the Schrodinger equation. This is not Schrodinger equation. No, not this one. This is what I am about to write. It's not Schrodinger equation. This is not Schrodinger equation in the sense this is the time independent part, and you can see it can have real solutions.
Because
there is no I. Even though psi is defined in a complex field, you can choose to work with real functions for time independent. There is a theorem, and you can see this from this. Intuitively, you can guess this is true. However, in the upper equation, you cannot do that, and it is not always. You can always do this. You can always reduce it to eigenvalue. This is the eigenvalue problem. Why eigenvalue? Because this is the eigenvalue and this is the operator, eigenoperator.
This is mostly for the eigen constant to play for the.
Okay, I think the problem above is that our independent variable in the example of we are using x as both dependent and independent variable.
X is both. I'm sorry, what?
In the above example, we are taking derivative.
Yes. It's on the same space. It's psi. Yeah. The two different.
The above one, the Newton's one, the Newton's one.
Yeah. This is the x. It is a psi.
No. I'm saying that we are taking derivative with respect to our dependent variable in that for that operator.
Dependent variable. What is the dependent?
PD. Yeah, the Newton one.
When the x, yes,
Yeah,
x.
is dependent variable, but we are also taking derivative with respect to x.
Yeah.
I think that is where the confusion is.
It's not a confusion. It's just the structure of the. Schrodinger equation is linear equation because. No, it's for PDE. It's the applications of differential calculus. So everything is in there. Okay. Any other questions? So all the PDEs you can think of, Laplace's equation, Poisson's equation, they are all applications of these things. But however, we will not delve into them. We will, however, mention one interesting thing. So ODE versus PDE. So all the tricks, all the methods of ODE can be borrowed to PDE with a higher level of difficulty. So this can be illustrated by a simple example. So this is first order ODE. So when I say prime, let me just make this. This is an ODE, first order linear ODE, and it has a solution. The most general solution is some constant, which is really a real number. Okay. Now, for a PDE, you need actually more than one variable. So let us work with two variables. This most general solution is actually something which is not a function of x. This is a 0, yeah. Okay, this is a function of y. Yeah, sure.
In the ODE case, ODE is only one.
Yeah, there's only one variable. For if PD, you need to have more than one variables by definition. Okay, so you're setting, when you take a partial derivative, you always set one thing to be constant, no? Y fixed with respect to x when you're doing. So the solution is, most general solution be some function of y. So,
It is actually full derivative, not no question.
I'm sorry.
So ODE is full derivative.
Yes, it's a full derivative of a single variable. Now, this is an arbitrary function instead of an arbitrary constant. Okay, and how many functions can you write down that satisfies this equation? Infinite. One simple example would be like e to the power cy1, say, or cy, sorry. Okay. Here c is arbitrary, and you can write any other function with it. Sine y, you can write anything. I haven't imposed any initial condition. So everything for the moment is a solution, which is a function of y only. So it is infinite dimensional. Okay? So the solution is infinite dimensional, even for the simplest of the cases. That's why people say that wave function lives in infinite dimensional space. Why? Because it's a function instead of a constant. It's a PDE, the solution of a PDE. So the difference between ODE and PDE is, in ODEs we find arbitrary constants for every order. First order we have one arbitrary constant. In second order we have two arbitrary constants, and so on. For PD is the same story. However, these are arbitrary unknown functions. And functions are by definition defined at every point. So they are infinite dimensional. Whenever you talk about functions, they are infinite dimensional.
So for ODE we can have only one dimension. Or
Yes.
The order of the ODE defines the dimension.
No. Order of the ODE defines the dimension? No. But I'm sorry, what?
Order of the ODE, like say, is second derivative.
No, this is not, no, the dimension. What did I say?
You can have a higher order ODE.
Higher order ODE is a different thing than dimension. What do you mean about dimension?
You were saying that we can have arbitrary constants, then we can.
Arbitrary constants are always one-dimensional.
ODEs, when you integrate them at each step, you get an integration constant, right? PDEs can have hard, if you integrate with respect to one variable,
You get another.
you
Yes.
can have several, you can have derivatives with respect to other variables as well. But if you don't integrate that, then if you integrate with respect to one variable, then instead of the integration constant, you get an arbitrary function, which is a function of the other variable or variables.
When you have more than other dimensions. So in PDE, other dimensions come in. So ODE is just a single dimension.
A lot of times in mathematics and physics, you will see that important PDEs, if there are symmetry of the problem, if there's enough symmetry of the problem, that PDE will decouple or decompose into independent ODEs. So, for example, if you have a spherically symmetric, if you could consider Schrodinger equation in a spherically symmetric potential, you will see that.
Well, that's a math trick. Yeah, that's a math trick as well. But separation of variable trick. If it is applicable, then you can reduce the PDE into.
Whatever the ODE PD classification.
Yeah, the ODEs are going to be. This will be discussed in our. PDEs can be made into ODEs, and you can just.
Under certain circumstances.
Yeah, with the separation of variables trick.
For example,
If you can write down a separation of variable.
and it always depends on the symmetry of the problem.
Yeah. So okay, so let's collapse collapse many results into one theorem. So this is the theorem. This is for a single PDE. Okay, so first order PDE. Let me write it down. So G be a let G be differentiable on R1. So whenever we use the word differentiable, it is in the total derivative sense. That means all the PDEs, all the directional derivatives exist, and partial derivatives also exist. And let F be the scalar field defined on R2 by f of x comma y to be equal to g of bx minus ay. Okay, where a and b are constants, not both 0. Then f satisfies everywhere in R2. Okay, conversely, every differentiable solution of, say if I call it equation 1, of equation 1, okay, necessarily NECSSARILY has the form, so let me call it 2, necessarily has the form of 1. Okay, the proof I'm not going to go through because I have already posted the proof, and the proof is essentially making the changes of variable and finding out various constraints and nailing it down, basically nailing it down to this. Yeah, I have, yeah. So one thing is easy to show, that if this is true, then this is true. And you just take the derivatives and you satisfy this. But one argument is very easy to prove. If you start with 1, you can always reach 2. Almost immediate, no? Take the derivatives and you say this is true. The tricky bit is, okay, so how to find this unique combination, just starting from the equation. So that's why the theorem is constructed. Okay.
So in the equation 1, where A and B are what is the word?
Constants. A and B are constants. Yeah, I'm writing it a bit fast. Constants, not both 0. One of them could be 0, but then, well, not both can be 0, depending on the problem. Okay, good. So one nice example of this thing is called Euler's theorem on homogeneous functions. Homogeneous. I forgot. Genius. Any US or? Yeah, very right. Homogeneous.
Homogeneous and non.
Yeah, spelling. I forget.
It's spell the way it's pronounced.
Yeah, this is one of the cases.
One of the rare
Rare cases. Guarantee. I always forget how guarantee is. Guarantee. GUA. Again, I forgot. Yeah, GUARANTEE. Yeah, right. Guarantee. Okay, so Euler's theorem on homogeneous functions. Okay, is that theorem here? Yeah, it's here. So the theorem is this: let f be a scalar field, differentiable, on an open set S, that is a subset of some Rn. Okay, f is a homogeneous function of degree p over S if, so always the region is there. Okay, all the lessons we learned is that you can only talk about in a certain region. Okay, not true otherwise. Okay, if f of tx is equal to t to the power p f of x, these are vectors. Okay, then this is called a homogeneous homogeneous function for t must be positive, and for any x which is in S, and well, for any x in S, well, I think I have to use the and again, so I have this comma, and for, let me do this. Also in S. So even though t is greater than 0, t cannot be something which takes you outside the region. Tx must be also in the region. So t is something like an epsilon here. I have to review a little bit.
So this is the definition.
This is the definition. This is the definition. This is exactly the definition.
Not a theorem.
Not yet. Then Then comes the theorem. Then the theorem is this. So, do I have a preamble? Yeah. There is no such preamble. Then no such non-trivial statement in the preamble. That's the Euler's theorem. And then F can be expressed as this. F satisfies. Then F satisfies.
DVP
Yes.
just multiplier.
Yes.
Dot product.
No, P just multiplies. Dot product on the left side, yes.
X dot
Yeah. He was talking about P, which is just a
cost.
exponent. P is just it's exponent, it's just a real number.
It's not an exponent.
It's not an exponent, it's just
It's just a multiplier.
In this case, yeah, but it's the exponent of your
Exponent of the function.
exponent of the T in the homogeneous function.
it's the exponent of the scale factor.
Scale factor. Yes.
Anyway, I mean, if you take the function x squared plus 2xy plus y squared,
Yeah.
you know it's a homogeneous function of the two. So,
That's true.
so the point becomes obvious.
Yeah,
This is the function.
that's true. This is you can use this function in the case of. So if you want to prove Pythagorean theorem, you can use it.
Pythagorean.
Yeah, you can use this one. Sorry. Oh, it's not. Actually, it's very intuitive and very simple because these are the angles are going to be the same. You scale it, the angle is the same. So the area just picks up the factor.
I think Einstein had his own proof of it.
Yeah, maybe. Yeah. So, yeah. So this triangle, this triangle, this triangle all have the same law, same Pythagorean law. If you can prove for this one, you prove it for all of them. Okay. Okay, so that goes by the name of Buckingham Pi theorem, but okay, we don't have time for that one. Okay, cool. So proof will rely on chain rule. So define a function g of t. I think I chose the wrong color. Yeah, it doesn't make much difference there. G of t to be f of tx. Okay. Now recall that g of t, when it is defined, when g of t is defined to be f of r of t, remember? Yeah. Then we found this result.
So is it vector function?
Yes, vector valued function. We found this one, no? Okay. Now we are going to do the same thing here. So if you take 1, so we find from 1, equation 1 is g prime t is equal to gradient of f x dot x. Okay. So that's equation 2. Now again, from equation 1, using the definition of a homogeneous function, we find the following. What do we find? So we have a g of t, but now I'm going to use the expression this as a definition of homogeneous functions. And then I take a derivative of it. My equation 3. Okay. Now set t equal to 1 in equation 2 and equation 3, and we find that's the proof. Yeah. He was right, yeah. I'll say later. F bar, no, not F bar, because F is a function of X, it's not a function of T. So the derivative is going to be F prime, I think you're looking for. Bar would make it a vector fields. Okay. So the converse is a homework. Converse of Euler's theorem is a homework.
Can you state the converse?
Well, you have this and then you prove that this is a homogeneous function. The solution, yeah. So that's the converse of Euler's theorem is left as an exercise. Typical math quote is left as an exercise for the reader. Okay, so next thing is another application, and this is the, can I scroll up? Yeah. D'Alembert's. So this is going to be subtopic what? Subtopic 2. So our subtopic 1 was to talk about the applications of differential calculus in PDEs. We wrote down one theorem and we gave an example. And now D'Alembert's. Is that how I defined it? I called it a topic. Okay, so this is the heading topic. This might be the different topic. Or is that not a different topic? No, this is the same topic, yeah? This is the same topic. Because still in the partial differential equations I am. Oh, categorizing is so, it's a menace. Even though it's trivial, but it's a menace. D'Alembert's solution of the O-wave equation. So I'm going to state the theorem. I'm not going to prove it. The proof follows the same flavor of argument that we used to prove the earlier theorem. We make a linear change of variables. Okay. And you use the first order solutions. I posted in the Slack details of the theorem. This one. But this also it should be a good exercise for you to also go through the apostle's arguments. Let f and g be given functions such that g is differentiable and f is twice differentiable, okay, on R1 or on R, then a scalar field F has the following form. Okay. Which satisfies this. Okay. With okay. So let me give it. So
Is that C or D?
is that C? It is a C. Which one is this one, right? Exactly. Yeah. Thank you. Conversely, any function f with mixed partial derivatives which satisfies 1 and 2 necessarily, and it's C-double-S-A-R-I-L-Y, has the form 1. 1 means what? The expression. So that's the converse. Okay. Okay.
D2 with second derivative.
Yes. Second derivative means, no, I'm sorry. Derivative is the second argument. That is t. Not second derivative. Derivative is
df by dt.
what?
df by dt.
Yes. df by dt. It's the velocity energy of the wave. So this is the second order equation you need to specify. Yeah. 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 So to understand those meanings of the words, you have to go through the proof a little bit. You have to see that how it really gives you this result. Why we demanded this to be just differentiable as twice differentiable. Okay. So next we are going to go directly to implicit differentiation. So this is the application in the differential equation, partial differential equations. Okay. Next topic is implicit differentiation. So there's going to be one topic, I think. Even combined with all of them, perhaps. So what is it? So say we have a surface. We have a surface, okay, defined implicitly by this equation, which is f x y z equal to 0. Okay. So we said this is an implicit representation of the surface. Okay. So for example,
Can I interrupt you?
yeah,
Is that has the form 1 or 3? It satisfies 1 and 2. This really have the form.
exactly, satisfies good one, which has derivatives, which satisfies 1 and 2 and 3, which satisfies 2 and 3. 2 slip of everything. Sorry. I probably thought in my mind I gave them 1, 2, then but okay, even if I've made a mess, you can realize that when I say satisfies, it must mean that it has the form. Yeah. Inconsistencies are also constrained. So this is a sphere, which is implicitly defined by the. Now, in this case, so what is the problem that we are trying to address here? The problem is if you want to express z as a function, that is one variable. So if you want to solve for one variable in terms of the other two, okay, it might not be always feasible. It might not always be easy to do that. Given a complicated surface equation, you might not be able to solve it for a particular variable. So in this case, this is possible because it's simple. It has two solutions. One of them is the upper hemisphere, another is the lower hemisphere. So z equal to plus square root 1 minus x square minus y square is the upper hemisphere. And z is equal to minus square root 1 minus x square minus y square is the lower hemisphere. Okay, so you have this. So the upper hemisphere is 1, described by this, and the lower hemisphere is described by this. Okay. Good. However, let us take this one. Okay. Now solve for z. Sure. Okay. Now solve for z. It's not always easy, no? I can make it even more horrible. I can make it as horrible as I want, right? And it's not going to be easy. So, yeah. So simply from here you can say this is not easy. On one side it's impossible, but it's not easy. So what we are really looking for is not really, well, so what do we want? We want to know the rate of changes. We want to know how things are changing, how the slopes are changing, first derivative, second derivative. We want to know these things. Okay. So to get those information out, we really do not need to know the exact functional relationship. How z depends on x, y, an explicit form is not required really. If we are really looking for the changes. Does it make sense?
The changes with respect to what?
Variables, x and y. You have some surface as you move away from, as you move in different directions. How much?
You're saying the tangents?
Yes. Slopes, tangents, yes. They are higher orders. It gives you the information of the surface itself. These derivatives gives you the information of the surface itself. Yes. So you want to climb. You want to know which is the steeper region, which is the less steeper region. You want to avoid the steeper region. So those information, to extract those information, you don't exactly need to know an explicit function. The derivatives will do. So that's the philosophy of this, methods, of these methods. So, however, judicious use of chain rule makes it possible to find the partial derivatives of zxy in this case. Okay. Naively, one might think that if you have a function, only then you can find the partial derivatives. If you have a functional relationship, then it's easier. But here in this case, there is a bypass road. You do not need to have an exact expression for the function. Still, you can talk about partial derivatives systematically. Okay, good. So with this motivation, let's begin this journey. So let f x y and some function of x y equal to 0 for some x y representing a surface. Okay. The sum xy, when I say sum xy, this means really that this xy is in the set, open set S, which is a subset of R2 in this case. Okay. Now let z equal to f of x comma y and implicit, I think there is no either, implicit representation of z. Okay. Let G be an auxiliary function, okay, defined by this thing. G of x comma y is equal to f x comma y comma f of x comma y. It has always been the theme, no? It has always been the trick.
In single variables.
Every case, we define something else. We have something, we define something else, then we find everything else with the help of that something else. Even in the proof of the D'Alembert solution, you'd see that you just, from out of nowhere, you come up with U and V for no particularly good, there are good reasons, but naively you don't see them. Then you see, okay, you impose some constraints that is well motivated, but initially you can't see them. So you bring in some variables, then you say, okay, let us have this function independent of these variables that satisfies some derivative zero conditions. Then there comes the constraints, and somehow magically it solves the equations. Because you didn't, but magic means, okay, so then you have an explanation why it worked. You have seen through in your head it works, then you understand, okay, because of this I can do this. But it's not a very straightforward road, okay.
Some sort of imagination.
Yeah, some sort of some of figuring out requires, yeah. Okay, good enough. So so we always did this actually. Throughout all of them we always define some auxiliary function. What happened to this one? Sir, I might have lost the pen.
No, you
Just attach it.
Our pair problem.
Just attach the pair.
Attach.
Attach.
Attach. Yeah. I think it goes here.
Yeah, somewhere around here. Where is it?
Already no, yes.
Attach it. Apply pen. Yeah.
Now,
Yes, no. It takes some time.
after
Yeah?
Otherwise, the pen becomes unfair.
Yeah. Specifically what I did that made it impaired.
No, it's not your fault. It just happens.
Oh. Usually pretty robust. So what is this? Okay, so this is trivially 0, no? Why? Because the function itself is 0. Now, if you define 0 by something else, it's also 0. That's why it's trivially 0. Now, what does function 0 means? That is all is partial, all the partials. Something is wrong. So all the partials should also be 0. All the partials of G are also 0. Okay. 0 in S. Good. So that means that the x of G is equal to dg, y of G is 0. Now, again, let more redefinitions. You have u of x comma y, u1 of x comma y, u2 of x comma y, u3 of x comma y. Okay, where u1 of x comma y is x, y. Okay. Okay. Now what do we find? We find, take the derivative of the dg dx, okay, that means take the derivative of g with respect to x, and use the chain rule. So I'm going to go ahead and write the chain rule. Let me know if you do not get it. Okay. From these conditions, I can write, I'm sorry, let me understand one thing properly. I made a mistake here. These are not, something is wrong with the pen today.
No, it's become a E. It's become an eraser.
না মানে মানে এটা হঠাৎ করে চলে যাচ্ছে
Maybe the surface.
Oh, that might be. Thank you, sir. Expert touch.
And it became short classical BBC.
Yeah. Well, if I write f prime, it might be a bit misleading. Okay. So, what do you want to find? You want to find the change of the function with respect to x. No? This is what we sought after. We are finding it in terms of some other things, where for this to make sense, the denominator cannot be 0. So let us just look at what we have achieved here. Okay.
Is D3 differentiation with respect to
Z.
Yes. So you are going for
Okay, makes sense. Yeah.
U2, that will become 0.
Yes, it becomes 0 because u2 is y.
So we are not counting the x.
Yeah. Well, actually, 1, 2, 3. They are not derivatives of x, y, and z. They are not. They are derivatives of just for u1, u2, and u3.
There's no c.
No, money. Okay, so what is the chain rule? You have u1, u2, u3, no? And you take a derivative with respect to x. So what is happening? That so function changes if the argument changes. Okay. That's what we're doing. All right. So yeah. Very good. So similarly, or by inspection, this is simple one. By inspection, you can see what the next one should be. So I would say D3F would be down and D2F should be here. This condition also applies here. So if it is not 0 for this one, this applies for the lower one. It's just kind of a no-brainer, no? Am I right? Are you sure? Am I right?
There should be.
Yeah, because df dy comes with that, and everything x part drops off, and the d3 is the right side. So yeah. And what about this? This is not there. It's not there.
Because z equal to f.
Yeah.
F is z.
Yes. So it is trivially 1. So yeah. df dz is what? The capital F, because previous two are 0. So du3 dz. Okay. So that's actually not going to give you anything. So this is like a ddf, df, and it's 1. If you define z equal to xy, a function of xy, that's 1. But it's not really going to give us anything. So this is not, we're not going to write it this. It's not going to give us anything. Because this is not the point. Writing it, you can write it, but it is not the point. Why it's not the point? Because z is expressed in terms of f of xy, no? So implicit differentiation. So taking with respect to z is not the point. Okay, so let us apply this toolbox to an example. So you have y squared plus xz plus z squared minus ez plus, we had 6, let me say c for anything. Okay, so same thing, but doing in more general ways, showing the power of this construction. Defines z, this expression defines z in terms of f of x comma y. No? Okay. Can I shrink a little bit?
No. Can we define z equal to x?
Yes. Define z. Yeah. But we cannot write an explicit formula, but it defines z. Yeah. Find c such that f of 0 is equal to 2, which basically means z equal to 2. Compute df dx and df dy at the point 0 comma e. Solution. So I sometimes have solution like this, but you can be just more general and write solution. Okay, so first thing, this verification is the first thing, and it's very simple. Just plug in the values. So if I call this equation 1, plugging in x equal to 0, y equal to e, z equal to 2 in equation 1. What do we get? We get e squared plus x equal to 0, so that's drop off, z squared, that is 4, minus e to the power 2 minus c is equal to 0. E square cancels out, so you have c equal to 4. First thing is verified. Now compute the partials, but that is just a simple thing to do. You just compute this thing given by the formula df dx divided by df dz d3, no? Okay. So u1 is x and u3 is z. Okay. So what is this? I left for the exercise because you can do this. It's going to take me 20 minutes to figure this out. And then you plug in these values, and then you have expression. Okay. Which will be, because it's worked out, the end result is beautiful. It's beautifully simple. Okay. So this can be done for any arbitrary function or a surface, function describing a surface. Okay, so we can group all these things into a theorem. Group all these observations into a theorem. Yes, probably theorem. Probably the theorem between. Yeah.
You said c equal to 4. C equal to.
See, find C such that. I haven't said anything about C. Yeah, so you might say, okay, why did I use the? It's not show that, no. ठीक है.
Are we supposed to do it? Or no?
We're supposed to find, compute. It's not a theorem. Yeah. So we have a proof. This is the proof for two. The case for R2. Z. Well, the function carries 3 variables, but the z is a function of 2 variables. So we have a proof for that construction, but we can generalize it. Okay, generalize it for n variables. Okay, and n minus 1 implicit variables. Let's do this. So let f be a scalar field. Okay, differentiable. So you can say that is a scalar field that is differentiable on or in an open set. The poster writes on in an open set.
Prepositions are what distinguishes the native English speaker from those who are not native English speakers.
Is that so?
I think so. Preposition is just absolutely no rhyme or reason for prepositions.
That's true. I thought the scholars of English who are very good at English might be able to have a better grasp of the prepositional uses. Assume that the equation this defines, assume that, okay, defines xn implicitly. You see, I missed the word implicitly. That's why you're thinking that z is defined by that x, y square, y z. You're like, it's implicitly defined. Okay. If you're given an equation, you can always think that you can solve it for one variable. No, Theoretically, you can solve it for one variable. Practically, if you can really explain it, it depends on how good you are or your computational prowess. Here we're trying to show that this is not necessary. We don't need to know the function. Defines action implicitly as a differentiable function of how many variables? One less variable, no? Say xn to be, I think it's a small f. Okay. Then for, okay, this is not the end of the story. For all x12 minus the tuple in Rn minus 1. Not quite. And S minus 1. Then for each k equal to 1 to oh god. For each of this we have dk of f divided by dn of f. Where? Okay. That's the pressing for time. So the proof essentially follows the same argument we did for R2. Okay, so I'm not going to do the proof, but you can understand how the argument works, and you can reproduce the proof. So it's left as an exercise. Okay, nothing interesting there. You just follow through the arguments. Now the generalizations from one surface to two surfaces. So generalization to two surfaces. Okay, the method of implicit differentiation to two surfaces. So why you should be worrying about such a thing, or talking about such a thing, not forget about worrying about it. So let two surfaces with the following implicit representation. Okay, so there are two surfaces. So this is one of them, and this is another of them. Okay, now if f and, well, should I say f and g? If the surfaces, this is equal to 0 is the surface. If the surfaces intersect along a curve C, we may obtain a parametric representation of C by solving the two equations simultaneously for two variables in terms of z, or in terms of the third. I haven't defined what the two variables are, so there's nothing inherently special about z. Okay. Let x, so I'm going ahead. Okay. Okay. Does it make sense? You have surfaces, they intersect. When the two surfaces intersect, they intersect on a line. And we can find an equation for a line, basically. That's what I'm saying. Expand. C is a curve. C is not the small c, it is a generic capital C for a curve.
Curve means line.
Curve means it's okay. Curve means a line. It can be wiggle. It can be a wiggle. Technically, it's a map from an interval to R, n, wherever this lives.
It's a one-dimensional object, that's what you mean. It's a one-dimensional.
A curve is a one-dimensional object. Yeah. Okay, so let x to be this, y to be this. Okay. So what we're doing by solving the two equations simultaneously for two variables. Okay. So we're letting that we have been able to solve it. Let this is done. So I am expressing the two variables in terms of the third. Okay. For z, an element of some open interval AB. Okay. So let me make this more clear size that by solving what did I work. So let this is true, then we go there. So then we have f of, what did we have? We can write it down again, no? Okay? Rewriting what we know. There's no harm in that. Define.
These are all happening on the curve.
Well,
Yeah, it has to, right? Because,
mm,
so you're taking z as the parameter,
yeah,
as the independent parameter, and x, y, and z being points which are functions of which satisfy the constraint equation.
yeah, 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 yeah.
They can only be,
Yeah, because you solve it.
you can only have it. Are you still doing the sphere?
No, well, it can be a sphere.
He has two surfaces to start.
Oh, two surfaces. F is one,
Mhm. Yeah.
and
G is the other.
G is the other
what
one.
is so?
C is the intersection.
We are saying we solve that to find the parametric equation for the curve.
So that's the simultaneous solution of these two surfaces.
Right.
So what I'm asking is that are we on that curve that satisfies?
Yeah. Because we are on the curve. Confused? Yeah, why are we?
Two surfaces intersecting one curve. That's a C.
Well, in this case, it is obviously true. It is because this is a. So you are considering some two-dimensional stuff, two-dimensional surfaces. They're intersecting on a curve. Intuitive, no? If you have higher dimensions, that will not be a curve. Yes. Okay. Because you are able to solve it, you can express x and y in terms of z.
So
If you have three variables, you have two equations. So you have one independent.
So, okay, so how do you find the equation of the intersecting curve?
We are not. We are just assuming that this is true. For the moment, it's not needed for the construction.
And why is Z independent?
It is a choice. It could be anything else. Out of X, Y, Z.
Okay, which you're fixing the gauge.
For example, one of these plane is a plane like say YZ plane, and the other one is the sphere. So the intersection is a circle.
Yeah.
Something like that.
Slice circle. The boundary of this. Yeah. So moving on. Define f of, what is this? Right. Define it. No harm in defining again, no? F of z to be f. It is clear why it is a function of z only. Because everything is a function of z. And g of z is so then you take a derivative of it with respect to z. However, this is a function of a single variable. So it's a total derivative. And however, the right side you have some partials going on. That's it. Similarly, it's a capital X, by the way. Very good. আর 2 পেজ মাত্র 5 থেকে 10 মিনিট লাগবে বেশিক্ষণ।
Time dilation.
So I think there's some difference in the ways, so is it the same if they are like
I'm pretty sure they're the same. If they're not, we will talk about it. I might have, did I?
they're absolute rights, like I think the same.
F prime is same, yeah. But I'm writing it. Yeah. Because this has a single variable, yeah. Absolute right is a single variable, yeah. Right. Yeah. I'm avoiding the confusions as much as possible. Trying to. Okay, so this is cool, but that's it. That's it. We have solved the problem. What have we done? Let us plug in the values. No. Plug in the values. Plugging in the values. What do I mean by that? Solve this equation. Solve this equation. Solve this equation means that separate df, separate this term, the single term alone, and write everything else. So I'm going to say rewriting it. Rewriting. It's like these are the forced lines. Everything else is forced upon. Once you defined it, then everything is forced.
So what force?
These lines are forced.
Where did force come from?
Force comes from means that you are. It doesn't require you to use any more intellect. You just have to just change the sides and just. We'll see.
Do you mean force from physics?
No, from chess.
So force need to happen.
What?
These lines are these are forced lines. Yeah. They're forcing this to happen. Satiki will say. The definition is such that these lines are meant to happen.
Yeah, but when you are writing these, you are no longer on the curve, right?
Well, whenever I have this, when I am on the curve. Otherwise, I cannot start with this one.
Yeah. But
Okay.
when f and g are identically zero, then you are on the curve. Now you
No, they are integrally zero on the surface.
Yeah, but you want both of them to be zero.
Both of them are zero.
Simultaneous.
Yeah, both of them are zero.
So basically what you're saying is that the values of z in both of those equations are the same. They are not.
Yes, exactly.
They are not generic values.
Right. Because I can express x and y in terms of z only if I can solve it.
Yeah, but doesn't that simultaneous solution indicate that you are on that curve
Yes.
where they are intersecting?
Yes.
Now, see that when you are defining f of z to be that function,
Yeah.
you are not taking that to be zero, meaning that are you still on that curve?
I'm taking that to be zero.
Like a new one.
That's why I can solve it, no?
No. When you are defining f of z,
Am I taking this to be zero?
no, when you have both of them to be zero, then you are on the curve.
Then I'm
No, I mean he's defining f.
I'm not sure what
and
I'm
g.
I'm not sure I'm
He's defining
understanding.
small f and small g to be those
And
functions.
he said, if the book writes like that, those definition has to be zero.
Yeah.
So in that case, f of z is identically zero. What is the point of taking your derivative?
No, it's not zero. It's a non-trivial function of z. So it has to be solved for z.
Okay, that's right.
Right.
So and that's basically the curve. So you have a it's
Man,
it doesn't
the-
have to be identically zero. It's not a trivial function. What I'm saying is that it can be a non-trivial function of z. And
Man-
you can solve those two equations simultaneously. Now that's a very constrained equation. Right. Solving two
Yeah.
one variable and you have to solve two equations. So is there
It's on the
a
curve.
chance that you'll get overdetermined?
No. What did I mean? I'm sorry. How?
You have two equations, f of z is equal to 0 and g of z is equal to 0.
Right.
So you have one variable z and two equations constraints on them, right? So what I'm saying is that, could it be overdetermined? You know that if you have too many constraints, sometimes there's no solution, right?
So now when you set both of them to be zero, then it's good because you are still on that curve.
Yeah.
So everything is happening on that curve.
Yeah, that much I understand, but what I don't think it looks like that. If you forget about f and z, the new definitions, I'm not really doing anything apart from.
I'm sure there is a solution. I'm just trying to figure out. A geometric mean.
Yeah, that's what I'm asking actually. F of z equal to 0 means that the derivative of that with respect to z is also 0.
Yeah, that's what I'm saying. If I forget about these things, there's the same thing. So if I take a derivative of this thing with respect to z, it's 0 because it itself is 0.
Yeah.
So not over determination. It's just a rephrasing of the same thing.
So still we are on the curve. Right?
Oh, we are on the curve because this is what is happening. The z is determined by this thing. So z is not determined. I'm sorry. X and y are determined. That is independent. Does that make?
Yes, if you're defining x and y, it's
Yeah.
So everything is happening on that curve
On that
where these two surfaces
Intersect. Yeah.
It'd be good to have some examples.
Yeah, we will have an example.
Z equal to 0,
Spheres and
then x, y plane, and then one is a sphere.
Yeah.
And we'll have circle.
Yeah.
I think you will eventually lead to that implicit function theorem. Right?
Yeah. This will, but not today's class. So we'll find a solution. So we'll write it in a matrix form and use Kramer's rule. I almost wrote cruel. So matrix, matrix form, Kramer's rule. It comes a little bit later. So what happens here is that you write, so what we are after now? We are after what? We want to find these things. We want to find their changes. Okay, so
Differential geometry is responsible.
You generalize to yeah. In disguise.
we have a system of equations. Okay, yeah. So yeah, wait. That means it can be generalized. So Kramer's rule by Kramer's rule. CRUEL rule. So that's not rhyming. Back to linear algebra. There is no escaping linear algebra. Even though.
That's why we have multivariable and linear side by side.
Yeah.
Stop rational.
Yeah, this will become more clear in the next classes when we talk about saddle points and etc. More and more in the future. Okay, so the condition is that this cannot be 0. Determinant cannot be 0. The matrix cannot be singular. So So similarly, you can write down y prime of z, and that's what we want to know. So it gives you information of the slopes. So these are called Jacobian Jacobian determinants. Jacobian determinants are, so these are Jacobian determinants. They're defined like this. So you have, okay, so I will just use det of this thing, df1 dx1, df1 dxn, dfn dx1. This is a square because it's a determinant. Okay. So Jacobian matrix and Jacobian determinant are different. Jacobian matrix need not be a square. We met it before, no? Yeah. But Jacobian determinant is of a square matrix. Okay. So using this new notation, we can write it like this. We have I think the minus I missed here somehow, or didn't I? I probably missed the minus. d with respect to x comma y with respect to f comma g. Okay. Oh, I think I missed here as well. Wait a second, sorry. Yeah, this is a ratio of Jacobians. So I missed df comma g with respect to z comma y, and of f comma g with respect to dx comma y. Now this is correct. Forgot. Right. Yeah. Okay, that's good. So you can generalize this. Generalize this to m equations in n variables. Okay, obviously where n must be greater than m, and solve for m variables in terms of n minus m variables. Okay. Okay, so just want to start the next topic. Okay, we will not go very deep into it, but we're just going to define it. Okay, so this is the next topic, and the topic's name is extremum values. Okay, extremum values for multivariable function. So, okay, assume z to be f of x comma y. Yeah, it's going to be like 5 minutes. I'm sorry, 5 minutes, we're done. I'm just going to define them and we'll do everything else in the next class. Just to have a head start. Can be thought of a level surface, can be thought of a level surface of a scalar field f. Okay, that is level surface of f is equal to f minus z. Okay. So if f is differentiable, obviously not capital F, small f is differentiable, okay, then we can talk about this. Obviously can talk about this now. So capital F depends on small f, and if small f is differentiable, I can write capital F as like this, minus k hat. Okay. So far so good?
If it's a minus z.
Right. Then I'm taking gradient of the scalar field. Z is obviously differentiable. Now tangent plane at P1 is given by, now I'm going to just derive it. At a point, say P1, which has coordinates like this, x1, y1, z1, okay, and I'm going to derive it. It's given by, so we know how to find a tangent plane, no? At a point. So at a point P1, point is a vector dotted with x minus P1. That's the equation of a tangent plane. We know this, no?
Tangent plane at P1.
At P1, tangent plane at a point P1. So from that line to next line, what should be the next line? Just straightforward substitution. Okay. And I can write this because a minus sign is there. So this is our equation of the plane at P1. Okay. Now, equation of a plane, abstractly, then you can just say that, okay, equation of a plane can be written like this as well. So therefore,
Where is this point? That point is on the surface?
Yes, yes, at that point. On a
But at that surface, f is equal to 0.
capital F.
Big F.
Yeah, capital F, yes, yes. Zero set.
Yes. That you are taking gradient of the original function. Yeah.
Yeah. So I'm going to say just this is this, just by equating them. Okay. And y a and b is just a notation. Apostol writes it this way. He makes use of these words, and I'm actually cheating here a little bit. This এখানে আর্গুমেন্ট গুলো দিতে হবে আর কি. This is at that point x1 by 1. So আমি এখানে লিখছি আর পরে লিখতেছি না. Okay, not at every point, at that point. Okay, good. So what AB does, it makes is just so what is Z? Okay, so if AB and 0, if A and equal to 0 and B equal to 0, what happens? If you look at this equation, it's just this is x-axis, this is y-axis, and this is z-axis. This is just horizontal line. No?
It should be a plane parallel to the x-axis.
Yeah. This is a plane horizontal, horizontal to xy. It's a slice of that. It's a plane. So if okay, these are 0, then P1 is the stationary point of the surface. Okay, that's the definition. Or not okay. That's the definition, but we haven't really used the word defining it properly, but you can see that this is we'll do it in the next class, but yeah, this is the flavor of it, that if AB is 0 in such a plane equation, then you find that at that point, then that point is termed as a stationary point of the surface, and that point as well, this is the same point, is a stationary or critical point of the function f of x comma y. Okay. So this can be generalized for arbitrary variables, and stationary points of a surface. So what kind of point satisfies this? There's not just one type. There are 3 different types that satisfies this condition. 3 points of a surface are classified into maxima, minima, and the third one is called saddle. Okay. Its one-dimensional analog is the inflection point. However, well, it's not quite an analog. The interpretation is different. Zoom out. Yes. So these 3 things are like, one is a maxima of is a crest of a mountain. Another would be a valley of a sorry, not a valley. It would be the trough of a mountain, and another thing is the valley. The saddle is the most. So it is rising in this direction. Is right. Wow. Yes, it's a horse saddle or a chips, Pringles chips, sorry. And this point. At this point, you are going in this way. You are rising in this way, and you are falling in this way. So this point is a maxima for this direction, and minima for this direction. So when you're going this way, you are lowering down. That means this point is a maxima. However, in this direction, this is actually minima. It is there. মানে এখান থেকে নিচে যাওয়ার কোনো সুযোগ নেই, so you have to go up. So yeah, it's kind of funny. It's hyperbolic, no? So that's all.